Hi, my name is Manny Stringer, and today I'm going to talk about the contact process, basically how I make sulfuric acid. First of all, we're gonna recap what the contact process is, how we do make sulfuric acid, what is the problem with regular temperature reading and the control based on that, and what is the solution to fix all these problems. So let's go. The industry's way of making sulfuric acid, which is H2SO4, and we basically make that from sulfur, which is this, and we burn it. It is not directly made, but we actually burn it. So we make the first, there is sulfur, then we make sulfur dioxide, then we make sulfur trioxide, then we make sulfuric acid with absorption. The conversion here is burning, and the conversion here is a catalyst. The catalyst is V2O5, which is vanadium pentoxide. First of all, we have a burner, and if you want the whole process, you can search it up. It's on my channel. I have described it and went through this a lot, so I'm not going to explain it here. So what's the problem with this? This is not exactly the format, so the molar ratios are not perfect, but this is basically it. So 420 to 450 is the optimal range. So basically this is an exothermic reaction. This is the delta H here, and the minus is basically something, I don't remember the exact number, but what is important here is this 420, 450 degrees Celsius, the optimal temperature range, because under this, if we are lower than 120, so lower than 120, then we basically 420, we basically have a low conversion. If we are above let's say 450, then we have reduction back. That means we convert back the SO3 to SO2, and this is just low. So the problem are this. So this is why we need this optimal temperature range, if you are just wondering. So in the industry, they usually measure the temperature because they have a big enough pipe diameter that they can feed the thermal, there is like a alumina or L2O3, I believe, aluminum oxide or corund or whatever. This shit is a like a shield around the probe so it doesn't melt. And basically this is too thick for my little catalyst tube to go inside. My tubing is like this big, so it doesn't fit. So it's a big X. So for this reason, I can't do this, and I had to figure out something different. And I thought to myself, well, if they do this in the industry, what is another way that they do this? They basically use UV light, which is just going to use this. So they use UV light. So they use UV is around 200, let's say 50 to like 300, 300-ish, 320, let's say. So nanometers of wavelength. And this UV is basically a very specialty of the sulfur dioxide. Sulfur dioxide has a absorption rate, so it absorbs, and that is very important because it absorbs light in this range. This is basically light, but you can't see it because it is out of the spectrum. So we have the far UV here. I don't have violet, so far UV. This is the red on the other side, infrared, and radio bullshit, radio frequencies here, and this is like visible light, so this is like visible light, and this is UV and gamma, all these bullshit there. We want to use this is somewhere here out of the visible light, this range is here, and that's a really good thing, because when we have a pipe full of catalyst material, or just let's say here we have the catalyst, here let's say we have the catalyst material, here comes in the SO2 plus the air which contains O2. This reacts here at 4, let's say 430, and here SO3 exits, SO3 plus SO2 plus air, because we can't convert it all in one stage. So this is the catalyst here. And after that, here it comes, and what we do here is that we have a photodiode here that, or basically we have a UV light that generates light through here, and it has a UV absorbing photodiode on the other side, which is quite sensitive to UV and only to that. Basically, as the fog comes through here, so we have the little, let's say here there is the little SO3 molecules coming through here, and the SO2. The SO3 no longer has this affinity to absorb the UV light, so this here will be like, let's say I'm just going to draw a little trapeze, so it's going to like convert. This means that the SO2 like absorbs the emitted light's energy, and less light gets through here just in like quantity. So basically that's this amount. If we were to look at here on this side, I fucked it up, but let's say this is let's say here, so it's a little star there. So the star there signals another part, which is let's say this is the star. So we have the little atoms or molecules, sorry, coming through here, and there is the so there is the little this is the LED, this is the diode, this is also the diode D, and this is the LED. Not going to write it out. So here we have the same amount of girth of like intensity in this diagram, but here it is lower, this is like smaller, and then here, so less light can get through, because this is, and this is just a visualization, this doesn't happen in real life, but this is what I want to like signal, that if we were to use, because the photodiodes, PD, these give out, let's draw here, the photodiode gives out some voltage, and based on the resolution of your board, if it's like an Arduino, you can, I think, break it up into like 3.3 volts. If it's a ESP32, I think you can break it up into 5 volts. So resolution. So let's say this is like a number. You can like multiply it, but if the LED emits light, so this is the before, this is the after. So before we have that, the SO2 is not converted yet with the catalyst, but is more in concentration. So therefore we, let's say, measure like 100 score. This is just the score before. So before photodiode sends out 100. The after photodiode, on the other hand, will experience less of a SO2 concentration, thus that will absorb the light less, thus will read a higher score, let's say 200. The delta here will be proportional to the conversion, or the SO3 made. This is this simple. Of course, there is some nuance here that you basically want to like set a initial data, because let's say your photodiode is sensing 300 and they have like a different number when they run dry, basically when there is no thing coming in, so there is no concentration or nothing is coming in, then basically you have a different number. Photodiode PDA, this is not after, this is photodiode A, has a dry or number of like 100, let's say it's like 360. The photodiode B is, let's say, 400 on dry, and basically it slowly, when you start it, so this is time, this is the score, and when you start it, it goes up to this and it goes lower, or sorry, it goes lower, then it stabilizes. Fuck, this is really shit, but it goes lower and then it flattens out. So this is like, this part is here and this is like parallel. So there is some delta time here that you need to wait to be able to set the I0. This is like a theorem or something like that. It is called the Beer-Lambert absorption, I don't know what. So basically you have, I'm going to have the equation on screen. You have like a starting conversion, and you can calculate out the concentration of the SO2 in the tube based on the length of it, the light it travels through it, and the wavelength, and if there is some other epsilon or some bullshit coefficient here. So you, based on this, you can calculate the concentration. And we have three catalysts. So one catalyst here, let's say, so that, yeah, we have like a catalyst, let's go from left to right, catalyst, then we have an absorber and other things, dot dot dot, then we have another catalyst, then we have another catalyst, and then we have a, this is like a scrubber. So we take readings in concentration, because I bought a pair of, or a LED that has 4 LEDs on it, or LEDs, sorry for the shit pronunciation. We measure the concentration here, we measure the concentration here, then we measure it here and here. Based on these two, we can calculate out the first stage. Based on these, we can calculate out the last stage. This is the, let's say, third stage, sorry. And based on these two, we can calculate out the total conversion. This is like first cut conversion. This is like the last conv. Based on these, we can calculate out the total conversion. And based on this, or yes, based on these readings, we can see how much is coming still out. This is the waste also. Waste shows the waste as well. So that is really important. Based on these readings, we can create the system, and we have like a slow pulse width modulation, which means that we have like, let's say, 5 seconds let's say, let's go with 5 seconds. We have 5 seconds of time, and based on this, we can see our still have some waste here, so we need to increase the temperature because it seems like we are producing more sulfuric acid or sulfur dioxide that we can handle. We try to increase the temp with this. So we have a base timing. This is going to be the heat and the waiting time. So this is going to be heat. So let's say that's like 20%. So let's say 20% is, this is not proportional, but whatever. So 20% is going to be heated. The other is going to be rest. For this is, this is blue. This is going to be total red. So 5 times 2, that's 1 sec. 1 sec, this is 4 sec, off. This is on, this is off. And based on that, we can control with a relay the amount of energy or electricity goes into the heating coil with a solid state relay, SSR, just not USSR. So SSR with a solid state relay, we can control this, and we can increase this to, let's say, instead of 1 sec, we go to a 1.2 sec. So that's like a 20% increase. And we are going to just see what happens, and if it doesn't go up, then we are going to reduce this back. Then we have another system, which is the flow control, which is actually here. If I may just have a quick demo here of the flow control. This is the system. This is like a needle valve here, and this is just basically to be able to slide freely. This here is a needle valve. You can't see it. There is like an O-ring here, that there is like a tubular part here, and there is like a screw on here. There is going to be a gear, and it's going to, as the gear rotates, this slides freely. Of course, this is like hold in place, and it can basically, like, if it would work correctly, then it would be able to slide in and out, just the fucking, yeah, whatever. So it would be able to slide in and out, because this does this, as you can see, it does be able to slide, because this would just move it. So back to the actual point. So the flow control will be able to shut off some air from the burner. Basically it can completely, so this is the flow in, this is the bypass, and this is the bypass, this is the burner here, and these mesh together and they go into the catalyst section. So if the, here is a dry air, so if, and here's the needle valve, here's a needle valve, and here's another needle valve. Basically we can control the incoming air as well as shut off the total burner if need to be, or just maintain a lower flow control. So we can like totally cut it out or just decrease the amount of air coming in. That means we can like basically reduce the amount of sulfur burnt because we reduce the air, thus the oxygen. Then there is not going to be that much, so we basically decrease the oxygen. That's going to decrease the SO2, then that's going to increase our, and that's going to lower our waste. Basically we can convert a better amount. This is the system. As well as we can tune this and the flow control, and we can basically have a better conversion without any waste. And how we do this, if you are just curious, in real life, this is more of a tactical thing, but I have the little this photosystem in my hands. This is basically the system. If we take this this is the most complex part of the whole system. I'm just going to unplug this. This is a basic component. This is the quartz tubing. This is necessary for it. I haven't told this yet, but it's really important that we use quartz tube. The regular glass absorbs UV lights, thus you cannot measure it on the other side. So even if there is some light here and it goes through, it can't go through. It wouldn't be able to, even if there is or there aren't any sulfur dioxide in it. And it's like quite dirty for now. I will have to clean this out. So we have the, I'm going to take this off, going to have like a bottom part which has this little sensor. This is the photodiode there. This is the GUVA. I think it's 12SD or something like that. This is a photo board especially made for absorbing UV lights. And this has like a 3-pin thingy. This is the power, mid is the ground, and the third is the signal. This puts out some voltage that we can read on the Arduino, or ESP32 if you will. And here we have at last the little box. We have like a tube here that is like a cooling casing, and this was the original LED. It had like this long tubing, and it has like a slide in, slide out little thin bar. I can show you. I can like unplug it, and it's basically this. So it has like a rail inside. You can unslide this or slide this out, but I'm not going to, because it is quite hard to put them back. It's lost the focus completely. Yeah. So we have here, there's like the LED right there, which is it emits some UV light because the needed necessary UV lights, the 230 this 250 320 nanometer wavelength UV lights are, as I said, out of the visual range. It also emits some 430 nanometer lights, so you can actually see if it's on or not, because you basically can't see, and it damages your eyes as well. So you need to like wear some protective lenses or some UV absorbing lenses in there. So yeah, this goes in here. This is like a cable with the proper cable management. You can just basically put this back into its place. It has this little hole there, and you can see the LED in the light there. It basically shines through the tubing. This is basically just to get stuck, for it to be able to hold in place. As you can see, it lights and shines through there, and basically it illuminates the little GUVA here, and this slides on there. So it's like a real compact system. And this is another feature. This is just a long tubing. I will add another like Y joint here to split this. We are emitting some air because the system drawn here, so this is the system here, but before it comes here there is like a pump. So there is like a pump, there is a buffer, and here there is like a valve that emits air, because we produce, or the pump makes more. This is like a 10 liter per min pump. This is way too much for me, and here there is like a valve that is basically adjusted with a little tunable, like turn-in type of dial, and it is like a membrane thingy that if you turn it in, you lower the pressure that needs to be to be able to open. So it emits and basically like throttles the air, but it lets some escape. So with that, you can adjust the incoming air to a level that is healthy. Basically, this air is not wasted, because I use this air that would be emitted into the atmosphere and just be wasted. This is cold air actually. It is not. It has not been heated up yet. And guess what I do? I pump this into here and into there, which is very important because I don't know, because after the catalyst, there is, like, as I said, 400 degrees Celsius. Of course, the catalyst, the outgoing gas is not going to be totally 400 degrees, as well as it's not going to be able to like transfer its total heat, but it certainly is going to heat the quartz wool or the quartz tubing here that basically is here inside, and that has the possibility to heat up so much that it would melt the case and the whole thing would just collapse. So for this, I let the air into here and basically around the pipe here, and it comes out, and as well as into the GUVA's little chamber, and it cools the whole system down to a heat that is sustainable by the PLA. For this, that's why it is used like that. And as well as, yeah, that's the whole total reason. So this, and this is actually cooled. The before catalyst GUVAs, the photosensor here and here are not. They are not cooled. They are just, they don't have that little adapter there. So yeah, that would be the video. Thanks for watching. If you liked it, like and subscribe. All this bullshit, it helps the algorithm really. So yeah, thank you for watching. See you in the next one. Do the hard work, especially when you don't feel like it. Mwah.